Here we're going to do a little bit of everything. You see, here's our function, x squared. So let's take no special words for this, but let's just start somewhere. Let's go with okay. Let's go with zeros, our intercepts. Okay, intercepts. Let's do that first. Notice when f of 0 is 0, so there we have a point 0, 0. Um, there are no other x-intercepts. You can see that, and that is the y-intercept also. So that's done. Now let's check symmetry. Well, you can see this is it's an even function. We notice that. Now that's not going to happen on every function, but when it does, we'll take advantage of it. It's an even function, so you'll have that symmetry over the y-axis. So whatever happens, we can count on that. Okay, and you remember that's determined by taking f negative x and noticing that that's when you substitute in, you're just going to get this, which equals this, the original function. So when that happens, you have an even function. Okay, okay, symmetry over the y-axis. So take advantage of that when you got it. So number 3, let's go for asymptotes. Asymptotes. Let's see the verticals. Well, if they occur, it's going to happen here. If the numerator is not simultaneously 0. And this will happen at x equals plus or minus 3. So we have some vertical asymptotes there. What about horizontal? Well, you'll have to find this limit. Plus or minus infinity. Okay. Now, there's only going to be one for this since it's a rational function. And this will be a 1. So we do have y equals 1. That's a horizontal asymptote. Okay. Now, 4. Let's look for extrema. Are there any? Well, let's find out. F prime of x is going to be a 2x times an x squared minus 9 minus a 2x times an x squared. Derivative of the denominator times the numerator. This was numerator's derivative times the denominator, and then divided by the denominator squared. Okay, that reduces to, let's see, you're going to have a 2x to the third minus 18x minus 2x to the third x squared minus 9 squared. That is just negative 18x over x squared minus 9 squared. And you can see that that's equal to 0 at x equals 0. So we do have a critical number there. Now it's up to us to try to test what is that number? What does it do? Is it a maximum? Is it a minimum? So let's try out. That was slow motion. Okay. So you have your choice. You can try your second derivative test. I'm not going to mess with it. I'm going to go with the first derivative test. It seems like it. We've already got the derivative. Why should we bother? So stay inside those asymptotes. We got a negative 3, we got a 3, and we have, whoops, I got that in the wrong place. Sorry. That would be over here. We have a negative 3 and a 3, and we also have the 0 that we're worried about. So in here, this is f prime. This is undefined. This is undefined. Okay, does not exist at those zeros. Remember, this was critical. X equals plus or minus 3, not critical since they don't exist in the domain. Okay, even though you would normally check for those, I think it was fairly obvious that they were not going to be considered, but they are in my partition list here, and I will test around them. I'll test over here a negative 4. I'll test the negative 1. 1 and a 4. Now, the other thing is I really don't have to test both of these since I've got the symmetry going. But just for the practice of this, I will show you the results in here. So let's go ahead and practice f prime of -4. From your derivative over here, you're working with this guy here. It's our derivative. You can see the denominator is positive. Numerator will become positive, so this is positive. So we got a positive result in here, increasing function f. -1, f prime of -1. Again, this time you see another positive, since in this function, the numerator becomes positive when x is negative. Okay, how about f of 1, f prime of 1? Well, it becomes a negative, doesn't it? Okay, so now you got negative. Oh, by the way, here it's 0. Okay, that was 0, and it's negative over here. And at 4, f prime of 4, well, we will get a negative again, less than 0. So it's negative over here. So that tells you something. In here, we've got a maximum. It must be coming up like this. Here we've got asymptotes. Okay, so another asymptote here. Here it's decreasing to the right, so it must be doing something like this. And here it's increasing, so it must be doing something like that. Now we can put this all together on a quick sketch down here. So we have 0, 0. That turns out to be our relative maximum. And you have these asymptotes at plus or minus 3 coming in here. 3, -3. And you have this horizontal asymptote up here at 1. So I'm just going to trace that in. Okay. And I know the graph's got to come in here as a maximum, so it must be doing something like this. Heading down to the asymptotes. And it's back up here. It can't be coming in here. It's got to come down like this. This is the only way that the puzzle fits together. The pieces come in. And it's got to come down like this. And notice the symmetry. It's symmetric over the y-axis. So there's only one way this could look, and that's got to be it. It doesn't cross here, this asymptote anywhere, because then it would have to loop down and come back up, which it can't do, because that would require, for instance, let me just show you what that would mean. That would mean that it would be coming down like this, come down. It doesn't have another x-intercept, so it would have to bottom out somewhere and then come back up, and then head back up to that intercept. That would require another minimum in here, which it doesn't have. We already saw the only the only critical number was right here, which gave us that extreme relative max. So it can't do these things. It's got to do what it's doing here. We know that because we would have seen all the evidence otherwise. So that's all we need to do for that.